Hi, I'm Mark Barsamian. In today's video, I'll be discussing the quotient remainder theorem, the absolute value, and the method of proof by division into cases. This material is from the book section 4.5. It's titled Division into Cases and the Quotient Remainder Theorem. And the larger context is this sequence of sections in the book that are all titled Direct Proof and Counterexample. Let's review what's been happening in those sections. We've been discussing the following kinds of proof structures, proofs by giving examples, and then proofs that are general proofs, that is, generalizing from the generic particular element. And then we've studied and written proofs that involve a bunch of mathematical concepts. In the beginning, it was just a couple, even and odd numbers, composite and prime numbers. But then we each section have added a couple of mathematical concepts. So consecutive integers, rational numbers and irrational numbers, and the so-called zero product property and the concept of divisibility. Well, in section 4.5, we're going to add to our list of defined mathematical terms and concepts. The new concepts will be the absolute value function, and also concepts that are related to what's called the quotient remainder theorem. And then we're going to learn about a new kind of proof structure. Well, not really a new kind of proof structure, but a new technique in doing a direct proof. We'll start by discussing the quotient remainder theorem. So we'll start by considering a collection of equations, a whole bunch of true equations, an infinite set of true equations, and they all involve this green number 71 and this blue number 9. Notice, though, that within this whole collection of true equations, there's only one equation, that one, that satisfies this inequality. The red number 8 is greater than or equal to 0 and less than the blue number 9. Only one equation in that whole list that has that special inequality that's true. Let's look at another collection of equations. Here we have another infinite collection of equations. These involve the green number 72 and the blue number 9. They're all true, but only one of them, that one, has the special extra property that that red number 0 is greater than or equal to 0 and less than 9. Notice this equation looks pretty good. The red number 9 is greater than or equal to 0, but it is not less than 9. It's actually equal to 9. So among all these equations that are true, it's only the circled one that's the one that's got this special property going on. Let's look at one more set, infinite collection of equations. In this set, the green number is a negative number, negative 71. The blue number is still the blue number 9. Now these equations are all true, but only one of them, that one, satisfies this inequality. The red number, which in this case is the number 1, is greater than or equal to 0 and less than the blue number, which in this case is the number 9. So these three sets of equations and our observations about the special one in each set should convince you that this following theorem, the quotient remainder theorem, is true. The theorem says this: given any integer n, which we'll color green, and any positive integer d, which we'll color blue, there exist unique integers q, which I'm going to color in black, and r, which I'm going to color in red, such that this is true. Those letters n, d, q, and r make a true equation, And not only that, they satisfy this special inequality, that the red number r is greater than or equal to 0 and less than the blue number d. In a symbolic presentation that is written formally, the theorem looks like this. Here's our for any green integer n and any blue positive integer d, there exists a q and an r that makes all this stuff true. But there's a new symbol in this formal presentation. This symbol, the exclamation point, that's the symbol for unique. So there exist unique integers q and r, such that this equation is true and this inequality is true. Now there's some additional terminology that goes with this. The blue number, d, is called the divisor. The black number, q, is called the quotient. And the red number, r, is called the remainder. And notice that the quotient can be any integer, including 0. But the red remainder must be a non-negative integer. In fact, and of course it's got to satisfy that inequality as well. Now, I'm going to invent some terminology. I'm going to say that this equation is in special QRT form when it has the additional property that it satisfies that inequality. We're going to be often wanting to have an equation of this form that satisfies that inequality. Now there's a related definition of two expressions that use the words div and mod. So the two expressions are this symbol, n div d, and I'm going to color the n green and the d blue. Now, what's the usage? That is, what do n and d represent when you see this symbol? Well, you're only allowed to use this symbol when the thing playing the role of n is an integer and the thing playing the role of d is a positive integer. Well, what's the meaning of this new symbol, n div d? Well, what that means is the unique integer q that makes all this stuff work. So n div d just stands for the special q. There's another new symbol, n mod d. Now, when are you allowed to use this symbol? Well, you're only allowed to use this symbol when n is an integer and d is a positive integer. So that's the usage of this. What does it mean? Well, n mod d, that whole symbol, represents the special r. The special r in this special equation. The equation that's true involving n, d, q, and r, and has this inequality that's true as well. So here's an example. Question A. Find 28 div 5 and 28 mod 5. Well, let's color code these. In both of these expressions, I'm going to color code the 28 green. And I'm going to color code the 5 blue. And I'm going to color code the word div in black. And I'm going to color code the word mod in red. Because that will remind me that what I'm looking for here is the special q. And what I'm looking for here is the special r. So what I have to do is, the strategy is, to first write this special equation and then identify q and r. So our strategy is to write the special equation and then identify the q and the r that work. Those are my div and my mod expressions. So what is the equation that works? All right, so you see that we have our special equation that's in special QRT form. And so we just simply identify our Q and we identify our R. Those are what are being asked for. So whatever number turns out to be the Q, that's the value of 28 div 5. And whatever number turns out to be the R, that's the 28 mod 5. Okay, let's go on to question B. Question B is the same, except my n is negative 28. So the solution is we start by writing the special equation. We see that's our special equation that satisfies this inequality. So we have to simply identify our Q and our R. And that's the end of that question B. Now let's go up and recall what question C is. Question C is to find 30 div 5 and 30 mod 5. Well, our solution is, as before, we write the special equation. So there's our special equation. So our R is this number 0, and our Q is this number 6. And so our answers are just those letters. But remember which one is which. And that's the end of that example. Notice a couple of things, though. In question B, it turned out that our Q was a negative number. And we could actually have a question. Let's have a question D. Let's throw on another one. We could have question D that's defined 3 div 5 and 3 mod 5. So the solution here is to write the special equation. Notice in this equation my Q is 0. So that tells me that the answer to 3 div 5 is that it's 0. And my R is 3. So there's our answer. Now notice something interesting about these 4 examples. Well, these last 3 illustrate well enough. Notice that it's possible for Q to be a positive integer. It's possible for Q to be a negative integer. And it's even possible for Q to be 0. That's not the case with R. R can be 0. We've seen that. R can be positive. We've seen that. But R can never be negative, and R can't be equal to D or greater than D. So there's some restrictions on R, but there aren't restrictions on Q. Okay, let's go on. Example 2 says, suppose C is an integer such that that's true. Then what's the value of this? So C mod 13 is 5. So then the question is, what is 6C mod 13? Well, the key is that the only way to make sense of expressions like these are to think of the special equations. So our strategy is so from this given information that C mod 13 is equal to 5, we'll write the special equation involving C and 13 and 5. And then from that, we'll get a special equation involving 6C and 13. That's going to be useful for answering that question. From this special equation, we'll be able to answer that question by finding the value of r. So let's do that on the next page. So from the first expression, c mod 13 equals 5, all we can know is that the remainder is 5. Well, we know that the n is this unknown letter c, and the d is this blue 13, and q, well, we don't really know what q is. It's just unknown. Now we need to have a special equation involving 6c. Remember, the only way to figure out this is to have a special equation involving 6c and 13. So let's multiply this whole equation by 6. So look at that equation. It's in special QRT form. Notice that the number 4 satisfies this inequality. So this circled equation is an equation in special QRT form. And so this tells us that, well, in this equation, my n is my 6c, my d is the number 13, here's my I can't really call it q, but it's playing the role that is often called q, and this is my r. So from this I can conclude the following. That's the end of that example. 6c mod 13 is that number 4. That's the r. So now I want to turn our attention to how we'll use the quotient remainder theorem in proofs. We'll talk about that in a minute, but along the way it'll be useful to think about this question. Suppose that n is an integer. What does the quotient remainder theorem with d equal 2 tell us about n? Well, let's go back up and look at the quotient remainder theorem. The quotient remainder theorem says, given any integer and any positive integer d, then there exists unique integers q and r that make that equation true and that inequality true. But we're being asked about what this will say in the particular instance when d is the number 2. Well, I'm going to copy all this stuff down, but instead of this d, I'm going to write the number 2. So the quotient remainder theorem, just recopied but using d equals 2, becomes this sentence about the number n. There exists unique integers q and r such that n equals 2q plus r, and r is greater than or equal to 0 and less than 2. Well, think about this. If r is greater than or equal to 0 and less than 2, that means there are only 2 possibilities for r. Either r is 0 or r is 1. So in other words, I can rewrite that blue sentence without mentioning r. I can actually just use actual numbers. So this blue sentence, which mentions the existence of a q and an r that make all that stuff work, can be rewritten so that it doesn't have to use the letter r. There are only 2 possibilities for what r could be. R is going to have to either be 0 or 1. So here's the situation that would be if r was the number 0, and here's the situation that it would be if r was the number 1. The quotient remainder theorem says that one of those things is true. Exactly one of them. That's question A. Question B says, what does the quotient remainder theorem with d equals 3 tell us about n? Well, let's go back up and look what we just did. we copied down the quotient remainder theorem using d equals 2, and it became this sentence. Let's copy down the quotient remainder theorem with d equals 3. So the quotient remainder theorem says all this stuff. And the statement of the quotient remainder theorem with d equals 3 involves the existence of some integers q and r. But look, there are only 3 possibilities for r. R could be 0, or maybe r could be 1, or maybe r could be 2, but r can't be any other number. So let's recopy this big blue statement into 3 separate statements, each with one of the possibilities for r. So there we go. That big blue OR statement is the rewriting of the quotient remainder theorem in the special case where we use d equals 3. So instead of having to use this letter r and describing it by giving the restrictions in the form of this inequality, instead of having to use that abstract letter r, I just listed the exact 3 possibilities. The case where r turns out to be 0, or the case where r turns out to be 1, or the case where r turns out to be 2. So the idea is that the quotient remainder theorem, when you choose a value of d, results in you being able to say that there is an OR statement that describes behavior of your number n. So again, that big circled statement is a statement about n. Either this is true about n, or this is true about n, or this is true about n. Now, I want to talk about proof by division into cases. Now recall the rules of inference, which are just valid argument forms. These are from section 2.3 of the book. One of the valid argument forms is this one, proof by division into cases. It says this: P or Q is true. If P is true, then R is true. If Q is true, then R is true. Therefore, R is true. So that's the valid argument form. In the next example, we will use the quotient remainder theorem with divisor d equals 3 to prove this. The square of any integer has the form 3k or 3k plus 1 for some integer k. And we'll use the structure of the proof by division into cases. First, let's write this formally. So that statement, the square of any integer has that form, can be written formally as this. For all integers n, either you can write n squared as 3k for some integer, or you can write n squared as 3k plus 1 for some integer k. It won't be the same integer k in those 2 cases. Those are separate possibilities. How do we embark on a proof like this? Well, notice that this is a universal statement, so we have to have the proof structure of generalizing from a generic particular element. And that's got to be our start. Now, the end of our proof has to be that this whole predicate is true. So let's put that down in the very bottom. So that's got to be our proof structure, generalizing from generic particular element. Now, let's do something here. We want to use the proof structure, or we want to use the rule of inference that's the proof by division into cases. That's this. That means that we want to start by identifying an OR statement that we know is true. What OR statement could we use? Oh, well look, we're given a hint. Use the quotient remainder theorem with divisor d equals 3. Well, we know that we can get an OR statement out of that. This big OR statement is true when we use the quotient remainder theorem with d equals 3. It tells us this. So let's copy this whole statement and move it down. So there's our great big OR statement, and I'm going to justify this by saying it's by the quotient remainder theorem with divisor d equals 3. So let's go back up and look at our rule of inference for the proof by division into cases. We've got our big OR statement. Now we're trying to prove that some conclusion is true, and we've got that conclusion stated. So there's our big OR statement, and there's our big conclusion. So what we need here is to provide the middle stuff, the if-then statements that are the other parts of the hypothesis for the proof by division into cases. In other words, we have to do this. We have to prove that if P is true, then R is true. And if Q is true, then R is true. Well, in fact, we're going to have 3 of these because our OR statement has 3 parts in it. So statement 3 is going to be case 1. Suppose that n equals 3q. In other words, suppose that this is the thing that's true. So the way that we proceed is we start with one of the cases. We know that either that's true, or that's true, or that's true. So we start by saying, well, okay, so suppose that's the one that's true. And we go through a few steps that end by saying, therefore, the conclusion is true in that case. So these steps, 3, 4, and 5, amount to one of those. We've done one of our if-thens. That is, we've shown that if this is the one that's true, then the conclusion is true. So we've taken care of case 1. Now we need some more room because we need to do the other 2 cases. I'll insert some more space and move the conclusion down to the next page. Okay, so now we have to consider the second case. The second case is this case, n equals 3q plus 1 for some integer q. Well, then we just go from there. Now we want to get to the form either n squared equals 3k or n squared equals 3k plus 1. Well, look, we've got a plus 1 out here, so we're pretty close to the n squared equals 3k plus 1 form. So let's go for that. So in other words, we've got to rewrite this stuff so it looks like a 3k. So now we have to introduce our k. So we've introduced our k, and we've noticed that n squared has the form 3k plus 1. So that means that the conclusion was either this is true or that's true. Well, this is one that turned out to be true, so our conclusion is true. So steps 6, 7, 8 amount to another one of those conditional statements. They amount to that. If Q is true, then R is true. In other words, if you're in the second case, then the conclusion is also true. Now we need to consider the third possibility. It might be that this is the thing that's true. That'll be our third case. So starting with step 9. Well, then we just go forward from there and build n squared. Well, look, we got n squared equals 9q squared plus 12q plus 4. We wanted it to turn out to be either this form or this form. Well, the only thing we can possibly do is try to get this into that form. So we should break off a 1. So look, we've got this almost in this form. We wanted n squared to be 3k plus 1. We've got n squared equals 3 times this junk plus 1. So that junk has to be our k. So in our next step, we'll introduce our k. So we've introduced our k, we've confirmed that it's an integer, and we've confirmed that n squared equals 3k plus 1. So our conclusion is true in this case. So look, we now have a third if-then. Basically, again, if this is true, then our conclusion is true. So we're really ready to wrap this up. Our last statement is going to be statement number 12. I'm going to move the number up one little bit, though. I'm going to put it up in this empty space. So it helps the reader if you sort of wrap up the cases. You say the conclusion is true in every case. Therefore, you can say that that conclusion is true. That is, if you go back up to the method of proof by division into cases, that's this. You end by saying, therefore, the R, the conclusion, is true. So that's our first proof by division into cases. The other example of a proof by division into cases that I want to do involves the absolute value function. Now, most of you are comfortable with the idea of the absolute value when the thing inside is a number. So, for example, you know that absolute value of 5 is 5, absolute value of negative 5 is 5, and the absolute value of 0 is 0. You don't have any confusion about that. But it's a different thing to deal with the absolute value function when the thing inside involves variables, not actual numbers. So for that, you have to know that the absolute value symbol represents a piecewise defined function. That is, what the symbol means depends on what piece of the domain the x is in. So the definition of how that symbol behaves is a piecewise definition. Now, it's most often presented on 2 lines. I find it helpful to abbreviate it a little bit less. Say the absolute value of x is equal to x if x is greater than 0. It's equal to 0 if x is 0. And the absolute value of x is negative x if x is less than 0. So for example, so how do you compute the absolute value of negative 5 using this definition? You observe that negative 5 is less than 0. So we're going to use this formula to compute the absolute value. Absolute value of x is equal to negative x in the case when x is a negative number. So whatever my number is inside that absolute value, I stick on a negative sign from the formula, and I end up with the number 5. Okay, so prove that for every real number r, absolute value of negative r is equal to absolute value of r. Well, this is going to be a proof involving division into cases. Now, we know the proof structure. We have to have a proof by generalizing from the generic particular element. So we just have to say, let r be a real number. And we know how this is going to have to end. Proof is going to have to end that way. Now, what can we say about r? Well, we're doing the proof by division into cases, so we need to come up with some kind of or statement. So if r is a real number, we know that either r is greater than 0, or r equals 0, or r is less than 0. So we have three cases. So let's do the first case. Well, if r is greater than 0, then negative r will be less than 0, because I multiplied that true inequality by a negative 1. And so I got a new inequality with the inequality reversed. Okay, so then let's compute the absolute value of negative r. Now we have to use the appropriate formula to compute the absolute value. We know that the thing inside is less than 0. So when we compute its absolute value, we're going to compute that by taking the negative of the thing inside. Negative of negative r. So we've shown that the absolute value of negative r is r. Now we're supposed to compare that to the absolute value of r. Well, here again we have to use the appropriate formula. The appropriate formula is, well, we know that the thing that's sitting inside the absolute values is greater than 0. So we just use the absolute value formula that says the absolute value of this is going to be just r. And so we've shown that in this case, the absolute value of negative r is the same as the absolute value of r. Okay, so we've just done one of the cases, so I need a bit more space. All right, now we're ready for the second case. The second case is when r equals 0. That'll be step 7. So we can compute the absolute value of r, and we just get the number 0. Now let's compute the absolute value of negative r. Well, the absolute value of negative r just turns out to be, again, the absolute value of 0, so it's just 0 again. So our conclusion is that absolute value of negative r equals absolute value of r in this case as well. So we have another one of those if-then statements that we've proven. If r is 0, then this is true. Now we need a third case. The third case is when r is less than 0. That's this case. Well, if r is less than 0, then negative r is greater than 0. So let's compute the absolute value of negative r. We have to use the appropriate formula. Now, since the thing inside the absolute value is known to be greater than 0, when we take its absolute value, it doesn't change. All right, now what about taking the absolute value of r? So we have to use the appropriate form for the absolute value. Well, look, in this case, the thing that's inside the absolute value is known to be less than 0. So when we take its absolute value, we do it by taking the negative of the thing inside. So look, in this case, we can see that the absolute value of negative r and the absolute value of r are the same. They're both equal to negative r. So we have our third if-then. If r is less than 0, then that absolute value equation is true. So we've shown that in all three cases, the conclusion is true. So we're ready to wrap this up. We can number this last statement as statement 15. So the conclusion is that we've shown that absolute value of negative r is the same as absolute value of r, and the justification can be, well, just simply that it's because it's true in every case. That's the end of that example. The last example, prove for all real numbers x and y, absolute value of x times absolute value of y equals absolute value of xy. Well, I'm going to just provide the proof structure. So the proof structure is going to be generalizing from the generic particular element. So the first step would be let x and y be any real numbers. Or I should just say let x and y be real numbers. So that's the generic particular elements. Let's think about a big OR statement. So look, there are 3 possibilities for x, and there are 3 possibilities for y. So that might make it seem like we need to have 9 cases. Yikes. But really, we don't. There's a trick here. One thing to observe is that there's nothing special about the names x and y. So if we prove something that's true involving the letters x and y, we could just change the names to some other names if we wanted. So I'm going to circle the cases that we really have to think about. Case 1 is going to be where they're both positive. Case 2 is going to be the case where they're both negative. Now here's where it pays to be clever. Case 3 is going to take care of these 2 possibilities. We only really have to do one of them, though. The case 3 is going to be where either x is greater than 0 and y is less than 0, or y is greater than 0 and x is less than 0. It doesn't matter. You can just pick one and just say, well, I could change the names, and that takes care of the other case as well. The main thing is 1 is greater than 0 and 1 is less than 0. And finally, the 4th case is going to take care of all of these, all 5 of these. So case 4 is going to be 1 or both is equal to 0. All right, so that's the outline. I mean, those are the cases. It turns out that it's not at all difficult to do this for each of these 4 cases. If x is greater than 0 and y is greater than 0, then these absolute value expressions become very simple. If you know that both x and y are negative, then all these absolute value expressions become simple. If you know that x is greater than 0 and y is less than 0, these expressions become simple. So the idea is that in each case, the absolute value expressions become simple, and you're able to reach the conclusion. I won't go through the details because it would take way too long for a video, but you get the idea. Okay, that's the end of the video. Thank you.